Hello, and thank you all for attending today's webinar, Preventing Equipment Damage by Controlling Unwanted Energy, brought to you by Design World. We would like to thank our sponsors and presenters today, ITT Enidine Inc. I'm Mary Gannon, Senior Editor, and I'll be your moderator today. Just a couple quick housekeeping details before we get started. You will see several boxes on your desktop, all which can be moved around and resized to suit your preferences. You may open, close, and change the layout as you like. The webinar slides, as well as additional resources, can be found in the resource box, initially on the bottom right hand of your screen. The Q&A box will also be at the lower left hand of your screen, and that's where you'll enter questions for the Q&A session, which will come after the presentation. Feel free to enter any questions at any time throughout the webinar, and they will be answered after the presentation. If we do not get to your answer, our presenters may reach out to you afterwards. We also encourage you to tweet with us. Simply sign in through the Twitter box. Today's hashtag is automatically added to your tweets. If you have any questions on the ON24 system or need help, please refer to the help widget on the bottom of your screen. Finally, if you are watching this on demand, you can still use all the features, including asking questions. They will be emailed to us and we will forward to all of our presenters. Now please allow me to introduce our speaker today. Chris Kudla is a product manager at ITT Enidine, focusing on industrial shock absorbers and vibration isolation devices. He comes from an application engineering background at ITT Enidine and works closely with this group to identify product needs in the marketplace. Chris holds a bachelor's degree in mechanical engineering from the Rochester Institute of Technology and has more than 10 years of experience designing and implementing energy control devices in the industrial and automotive fields. With all that, I'd like to turn it over to Chris. Thank you for being here with us today, Chris.
All right, thanks, Mary. So like she said, my name is Chris Kudla, and I'm going to start by getting into the different forms of energy that I'll be talking about. And specifically, we'll be looking at shock and vibration, which results from the energy of motion. So next, we'll get into how to characterize that motion itself. We'll look at the physics behind the ideal solution, and this is taking a mathematical approach to finding the ideal solution. And then we'll look at which products are available to accomplish this. Finally, we'll get into the benefits which can be seen as a result of this analysis. So we'll look at this for single and repetitive impacts, and then also for vibration events. So let's get started with a couple examples to illustrate the type of shock and vibration events that I'll be talking about. So I've got a lot of applications shown here, but I'd like to step through and talk about how the energy of motion is seen in each one of these. So starting at the top left and the middle bottom, these are packaging conveyors. So in a scenario like this, we're looking at the starting and stopping motion of the item that's being packaged and how we're managing that energy when we're changing direction or stopping. On the bottom left, we have a motor and pump system. In this case, it's the vibration from the rotating parts that could cause damage to the equipment. That vibration that we'll be focusing on actually in the second half of my presentation. In the middle top, I have shown an automotive welding robot. So in this case, we're looking at the repetitive motion from moving automotive panels back and forth. This is a pick-and-place robot. And then finally, on the right side of the screen, I have shown an amusement park drop ride. So in this case, we're looking at the motion, the up and down motion of the passengers, and most importantly, the safety end stop that's at the bottom of the ride. So it's this safety stop at the bottom which would catch the passenger car in the case of equipment failure. So it's that type of damaging energy that we'll be focusing on. So from these applications, I'd like to focus on one vibration example, which is the pump in the bottom left, one repetitive start-stop shock event, which is the automotive robot, and then one single impact safety stop example, which is the amusement park ride. So I'll use these as examples throughout the webinar so that we can relate them back to these real-world situations. So let's start with the shock events that are from stopping. I mentioned we'll get to the vibration later in the presentation. So focusing on the start-stop motions, for the shock or the impact examples, type of damage we're preventing is due to the rapid deceleration of a moving mass. So in the case of the automotive robot, this is when the motion is picking the panel and moving it to the next spot on the assembly line. It's that starting and stopping that we're focusing on. So of course, the goal is to move the panel as quickly as possible to increase production speeds, but the panel could become damaged or the equipment itself could suffer if it's moved too quickly. On the amusement park ride, it's that emergency impact that we're looking at. So in the case of equipment failure, we need to manage the impact energy from a free fall event to protect the occupants. So one extreme example of this is the impact from a car crash. So in this case, each vehicle is traveling with its own energy of motion. And when they collide, the energy has to go somewhere. And this is the kind of damaging energy that we focus on managing through, in this case, non-destructive means. So the first thing that we look at is breaking down the components of the impact itself. So in each of these cases, I have shown a linear impact, a rotational impact, and that free fall event. And you'll notice that in every case, we have a couple components that are common between the three. The mass, the impacting velocity, and then any external driving forces or torque that's applied. So this is the first step in identifying how much energy we're dealing with in this scenario. Now, these parameters can be used to calculate the different forms of energy present in the impact. So starting with the linear impact on the left, we have both kinetic and work energy. The kinetic energy is from the mass traveling at its given velocity at the point of impact. The work energy is from external forces like the conveyor that's shown here, or it could be a pneumatic cylinder or something like this. In the middle case, we also have kinetic energy and work energy that are playing into that impact. Except in this case, it's a rotational example. So this would be like the automotive robot. So at the point of impact, at the end of stroke, we're again looking at kinetic and work energy, but in this case, the kinetic is from the rotational inertia, and the work energy would be coming from a motor or something like this. Then all the way on the right-hand side, we're again looking at kinetic and work energy that would contribute to the amount of energy at the point of impact. But we'll look at this in a different way. The suspended mass has a potential energy that's easier for us to calculate. And then it also has the work energy that in this case is due to the force of gravity that's pulling it down. This is obviously characteristic of the amusement park ride. So now that we fully understand the energy that we're dealing with from the impact, now the important part is to look at a solution to manage that. So the best example that I have to illustrate this is if you imagine someone tossing you a raw egg. Now, of course, if you just held your hands out firmly and didn't move them and just let the egg hit your hands, it's going to break and you're going to get egg all over the place. You wouldn't just hold your hands out like that. So instinctively, what we're all going to do is kind of cradle that egg. And at the point that it contacts our hands, we'll move it back and down. So we begin to cradle that egg, and by doing this, our hands displace some distance while we catch it. And this is what I'm showing here as the dynamic deflection. So I'm noticing on my slide that my equation's missing, but it's this dynamic deflection that's the one variable that we can change in this equation to calculate the output acceleration that the egg will see. So we're looking in this case at the impact velocity, dynamic deflection, and gravity. The impact velocity, it is what it is. The egg is traveling at some speed, and gravity is obviously constant. So the more that we move our hands and increase this dynamic deflection, which is in the denominator of the equation, the lower the output acceleration is on the egg. And this is the lower the number of G's that the egg will see. So that's obviously our goal. So the other component that plays into this that determines the amount of deflection that we'll get is the stiffness. So if you look at the arrow underneath the hand, it's that stiffness that is going to illustrate how much the hands will move. So if we hold our hands out there very stiffly, very firmly, they're obviously not going to deflect very far, and the resulting output acceleration will be high. With a very soft grasp with your hands, we'll get a lot of dynamic deflection. So in this case, the lower the stiffness, the higher the dynamic deflection, and the lower the output acceleration will be. So it's this stiffness value that we're primarily looking at to achieve the deflection that we need to meet the target that we have for our equipment for output acceleration and number of G's that it can handle. Now, to illustrate this graphically, we can represent the person's hands with a steel coil spring. And then in this case, the egg would be like the falling mass that's shown. So in case one, we have a stiff spring with short travel. So this is like holding your hands out very firmly. On the graph to the right, this is represented by the blue curve. So the reaction force is built up over a short amount of time, and it's the area under that curve that actually represents how much energy there is with that impact. So then when we look at case 2, it's a soft spring, but it has the same short travel. So on the graph, this is shown as a very much lower ramping up of the force. But at the end of that stroke, if we compare the amount of area under that curve to the case 1, it's much, much lower. And this means there's a lot of energy still left over. And you can imagine this is like holding your hands directly over a table when you're trying to catch the egg. As soft of a grip as you could possibly use, after a short amount of time your hands would hit the table and you'd get a spike in force. And that's what's being shown with this orange curve in case 2. The area under those curves still needs to be equal between each case. So finally, in case 3, what we're instinctively going to do with our hands to catch the egg, it's a long travel and soft spring. So this is shown on the graph as the same ramping up of force as the middle case, except we give it enough dynamic deflection so that the velocity goes to 0. So this is exactly how the forces on the egg are reduced when we're catching it. Now, another real-world example that I'd like to show is in train end stops. So there's a couple different methods that are used, and they follow these 3 cases that I'm showing here. The first, of course, being the high stiffness and short stroke. This would be represented by a rubber bumper. So for the rubber bumper, it obviously has a short stroke and it's very stiff. Case 2 would be represented by a short stroke hydraulic damper in conjunction with a friction brake. So in this case, the short stroke damper is very soft, like holding our hands over the table to catch the egg. But when it reaches the end of stroke, the remaining force then engages the friction brakes that are against the rail. Those take over with a higher stiffness, and not quite like I was showing in the previous slide, but in the graph to the right you can see that at the point of impact, case 2 in orange then begins to ramp up more, where the friction brake takes over. And then finally, for the long stroke and low stiffness, this would be a long stroke hydraulic damper. And you can see in case 3 in green on the graph that it's a gradual deceleration of the train. And the resulting forces are much lower. So now that we've determined the physics behind reducing the impact forces, the next thing that we need to look at is, after impact, how much will it rebound? So controlling the rebound is done with damping. So let's take a look at the same mass from the previous slide, and now we're going to drop it on products with various amounts of damping. So starting from the left, it's the same steel coil spring that we were looking at previously. A steel coil spring has very little damping. So when we have that mass suspended above it, we start with the potential energy from its drop height. Once the mass is released, that potential energy then changes into kinetic and work energy. As soon as it impacts the coil spring, as it compresses the coil spring, it's converting that energy into potential, stored energy. And then once it's completely compressed, the spring will then rebound it back into the air as kinetic energy. And that's shown between the blue drop arrow and the red rebound. Upon rebound, the scenario here with very little damping will rebound very close to the height that it was dropped to. With very little damping and low friction on the system, there's not much energy loss in this system, and it will rebound right back up to close to where it started. So now in the middle case, we start to introduce some damping. And this is shown with the spring damper there. So in this case, we have the same potential energy from that drop height. We let it go, it converts to kinetic and work. But now this time, when it impacts this spring and damper, we convert it to potential energy stored by the spring and thermal energy, which is the damper itself converting that into heat and dissipating it into the atmosphere. Once it's completely compressed, we will still have, in this case, some kinetic energy rebounded back into the system from that spring. Although you can see that it's not rebounding nearly as high as in the first scenario. So finally, all the way on the right-hand side, we have our same mass that's being dropped onto a system that's what we call critically damped. So the same potential energy converting into the same kinetic and work as it falls, except in this case, when it impacts the shock absorber here, all of the energy is converted into thermal and dissipated into the environment. So in this case, there's zero rebound. All of the energy is converted into heat, and nothing is put back into the system as kinetic. So by smoothly decelerating this moving object with low forces and rebound, there are a couple benefits that I want to go through. So on one hand, the dynamic deflection reduced the forces on the equipment. This means more efficient structure design less maintenance, less downtime, and higher productivity. During emergency impact conditions, it prevents damage and improves safety. This is particularly important for the amusement park ride example. Now, the damping reduces the rebound of the object. And you can actually see this graphically with the three curves that I have here. I'm pointing out the different amounts of damping. The pure sine wave there would be the coil spring. It just keeps bouncing up and down. The one in the middle is the middle with some damping, and you can see it degrades over time. And then finally, the critically damped hydraulic shock absorber comes to rest without any rebound. So in the production world, this means increased production speeds because we're managing those decelerations. So we can move faster between cycles and then not have to wait for something to stop rebounding before moving to the next process. This means cycle time improvements and cycle time reductions and productivity improvements. Now, here are some product examples illustrating the different amounts of dynamic deflection and damping. So starting from the left, and I tried to cover everything here with the amount of deflection and the amount of damping. So with the same steel coil spring that we've been talking about, we have a long stroke, which gives us the low forces, but very little damping, so high rebound. This is the one we've been talking about. Next to it, though, is a Belleville washer. So this, again, is a spring with very little damping, but it has extremely short stroke. So the rebound will be high from the low amount of damping, and also the reaction forces are going to be high. And as we move along, we have the automotive style damper, which has the longer stroke, but just some damping. So I have it as a medium rebound here. The rubber bumper, which is next to it, has the some amount of damping inherently, but the stroke is much shorter. So this will have a medium rebound, but high reaction forces. Then we have the industrial shock absorber. And this was our last example on the train slide to decelerate the train. So because the stroke is long, there are low reaction forces, and the damping is high. So I put low rebound here, but it's actually, if properly sized, it's zero rebound. And then finally, all the way to the right, I have shown a golf sand trap. So this is the case where there's high damping. So when the golf ball hits the sand trap, it doesn't really bounce much. It's dampened out. But it also doesn't deflect much at all. So the golf ball itself sees a high amount of G's. And that kind of covers the whole spectrum there. Okay, so now I'd like to take a step back to our original example so that we can shift gears here. And let's focus now on the motor and pump example, which causes vibration, a different form of energy of motion. So this vibration from the pump can be characterized in two different ways. On the top right, I have shown a scenario where the vibration is coming through the structure itself and causing damage to a piece of sensitive equipment that's mounted to that structure. In the other case, on the bottom right, the equipment itself is the source of the vibration, and this would be characteristic of the pump that I have shown. That pump, or the equipment that's vibrating, is causing damage to the surrounding structure, or it could be transferring through that structure to something else and causing damage there. But this is anything that has a reciprocating piston or moving parts like that, imbalanced rotations, and then there are a variety of different types of transportation vibration inputs. And these are a bit more complex, but they're a random vibration input. So in any case, we still approach it the same way. The goal is to isolate the source of that vibration from the surrounding objects. So the first thing that we look at is to break down what the vibration itself looks like. And now this is the vibration source that we're focusing on here. This is done by understanding the frequency and amplitude of the vibration source. So in the photo that I have shown, the example, the yellow arrow is pointing out the source of the vibration as being the pole. And the piece of sensitive equipment is mounted to the right of it and connected through mounts to that vibrating pole. So it's this pole that has a frequency and amplitude to it. This is the first thing that we're identifying here. Frequency is the number of times the vibration moves up and down each second. This is basically how fast the pole is moving. The amplitude is the amount that the pole itself is actually moving. So frequency is how fast, and amplitude is how much. A simple example to illustrate frequency and amplitude is a comparison of a hummingbird to an eagle. The hummingbird's wings move at a high frequency because they're flapping very rapidly. The amplitude is low since they're not moving very much. In comparison, the eagle's wings move at a lower, slower frequency, but they move much more, giving them a larger amplitude. This is what we're trying to identify for the source itself, so that we can then move along to finding an appropriate solution for isolating it. So now that we understand what the input vibration looks like, we'll take a closer look at the connection between the structure and the equipment. For every connection or mounting point, there's a frequency at which it will resonate. And this is called the natural frequency or the resonant frequency. So this is a bit tricky to imagine, but one example, and just as an example because it's difficult to relate to the mounts themselves, but if we think about having a mug of coffee, if you were to take that open mug of coffee and start vibrating it slowly back and forth, we all know that you can easily get a frequency, number of times you move it per second, that would not take very long to spill that coffee all over the place. So if we were to count the cycles per second that cause that coffee to really get moving and want to spill out of the cup, that's the natural frequency of that coffee. So a mount system has the same type of natural frequency. If you look at the spring mass examples that I've shown here, for each one of these you can think about pulling that mass down and releasing it. So when you pull the mass down and release it, how many times per second is it bouncing freely on its own? This is its natural frequency. So this natural frequency is characterized by the stiffness of the mount and the weight that's being supported. So in the example in the picture on the left, the weight would be that sensitive piece of electronics that's shown there. And then the stiffness would be how stiff is that spring that's connecting it to the pole. So for the four examples that I have shown here, the first two compared to each other have the same mass attached to them, but they have a different strength spring. So on the left, there's a weaker spring, and on the right is stronger. If you pull them both down together and let them go, the weaker spring will have a lower natural frequency than the stronger spring. Stronger spring is going to bounce much quicker. Similarly, we can see that on the right-hand side with the two examples that have the same springs but with different weights. So again, in this case, if we pull the two down together and release them, you can imagine the one with the heavier weight is going to bounce more slowly. This is a lower natural frequency. If we were to count the number of times per second that it bounces, compared to the lighter weight, will bounce much more rapidly. So this is how we characterize the natural frequency of a mounting system. And it's driven primarily by that spring rate, because in most applications, we can't really control the amount of weight that we're supporting. It's either that pump, the piece of sensitive electronics that I've shown here, or whatever else you're trying to isolate. So it's primarily that stiffness, that we can change that stiffness of the mounting point to put that natural frequency exactly where we want it to be to get a good isolation system. So in order to determine how much vibration will be transmitted from the source to what we're trying to protect, the vibration input frequency from the source is compared to the natural frequency of the mount or the connection point. And the easiest way to think about this is to take the two previous slides, our input frequency and our resonant frequency. And it's easy to think about it if you have the same input frequency and resonant frequency. That input will obviously cause the mount to resonate. It's like sloshing your coffee at exactly that point that causes it to spill. So now if we think about the same coffee cup sitting in our car, and when we're driving down the road, if you were to hit very, very small bumps all in a row, high frequency input, the coffee will jitter around, but it's not actually going to spill. You're not going to get those low frequency inputs that we know cause it to spill. So in that case, our input is much higher than the resonant frequency. And this is actually what we're targeting. So simply speaking, we're trying to avoid putting the resonant frequency of our mount system or our connection point in line with where our inputs are. So the measurement of how much vibration is being transmit is called the transmissibility. And I've shown that in the equation here, and I won't go through this equation, but it includes the input frequency and the natural frequency. And when we get a combination of input frequency and natural frequency that are far enough away from each other so as to not excite the mount system, we end up with good isolation. A low transmissibility is what we're targeting here. So not much of the vibration is transmit. This is shown in the top graph, where the red line is the input from the pole. And this is physically how much it's vibrating and moving up and down. And then if we were to measure what the response looks like on the electronics, that would be the blue line here, where with a low transmissibility, we're allowing the pole to move on its own without letting much of that movement transfer through the mounts to the electronics. And this is characteristic of good isolation. That's obviously what we're targeting. So a vibrating system with good isolation is characterized mainly by that reduced movement to the equipment that we're trying to protect. This reduction in movement lowers the strain on the surrounding structure, equipment, and mounting points. So it eliminates damage to sensitive components, prevents broken welds, and damage to the structure. This can also be an ergonomic improvement for equipment operators or passengers that are coming into contact with the equipment that's vibrating. The reduction in movement can also prevent disruptions to electronics, GPS systems, and provide a steady platform for cameras, video, and sensors. Now, since the focus for vibration isolation is on the stiffness itself, or the connecting or the mounting points, there's a variety of products available to tune a mount system to get the optimum isolation performance. So I've shown a few of the different types of products here. From the left, we have wire rope isolators. To the right of them are air springs, elastomeric isolators, and finally elastomeric coated wire rope isolators. And these products are all unique in their own way, but what we're primarily looking at is for the amount of weight that's being supported, which product is capable of supporting that, and then once that's decided, what stiffness do we need to keep that natural frequency far enough away from any of the input frequencies so that we get good isolation. And with that, let's open it up to questions.
Great, thank you, Chris. I appreciate that great presentation. And let's see what we have here. As I said again, please enter your questions in the Q&A box if you'd like to ask Chris any questions. In the meantime, let's get started with what we have right now. First off, Chris, do industrial shock absorbers really have zero rebound, and how does that work?
Yeah, so if they're sized appropriately, in the case of the automotive shock or some of the other damped components that I showed, it's the same amount of damping through the whole stroke. Whereas for the industrial shock absorber, it's pushing hydraulic oil through a small hole. That's what's creating that reaction force that we're seeing. So to keep it efficient enough that there's zero rebound, as you go through the stroke of that impact, or you stroke the shock absorber, it gradually closes off orifice holes to keep that damping exactly where it needs to be to prevent any rebound. At the end of the stroke, the velocity is zero and there are no forces that are pushing back on it.
Thank you. Here's one. You didn't mention damping in the vibration examples. Where does damping come into play there?
Right. So we talked about damping with the shock applications, and obviously that plays a huge role for shock. But for the vibration isolators, can imagine if we did have an input that was exactly at the point of resonance. So the pump is spinning at exactly the point that the isolators will resonate. A system that has very little damping will just allow it to bounce around and have a lot of rebound. It's that same tie to the rebound. But if we have a highly damped mount or isolator, then that point of resonance will be significantly reduced. And our output, while it's still something we're trying to avoid, it's going to be much less severe than it would be with a low damped part. And in fact, the products that I was showing at the end also have various levels of damping. So I can skip back here. For example, air springs have very little damping. It's just compressed air, compared to elastomeric isolators or wire rope isolators have quite a bit more damping. So this is also one of the parameters that we can tweak to get the system that we want.
Okay, great, thank you. Here's one that just came in. When you say natural frequency, do you mean the natural frequency of the isolator or the device to be protected?
So for the natural frequency that I was talking about here, it's the frequency that the isolator will resonate. Now, in other cases, the device that we're trying to protect will have its own modes or points of resonance that is an entirely different science of its own, but something that also does need to be considered. I didn't touch on that at all here, but again, that would be another point, another frequency that we'd want to look at when evaluating a system, if it's known, and try to make sure that that doesn't couple with any of the input frequencies. So if, for example, on a car, we're shifting the car through a couple different gears. Each gear has its own frequency at that RPM. If at any point that frequency of the engine and the gear is the same as, for example, the point at which the hood resonates, that would obviously be extremely bad, and it would cause the hood to obviously resonate. So that's a very good question, and something that is equally considered, but not shown in my presentation today.
Great. Well, I'm glad somebody asked that question then and that you were able to answer it. And finally, I think we have time for about one more question. So let's go with, what's the limitation on hydraulic shock absorbers? Why aren't they used on cars for crash protection, for example?
Right. So I showed that in one of the beginning slides, and one of the big drawbacks for something like that. Now, we put hydraulic shock absorbers on amusement park rides, is why I used it as a key example. But in a situation like that, the ride is being slowed by a magnetic brake in conjunction with a hydraulic shock absorber. In the case of crash protection on an automotive application, the impact velocities are usually much too high. So in that case, the oil can't physically start moving fast enough to give that damping, and it almost acts like a fluid lock, and in most cases the shock absorber would become damaged. So on a car, for example, for crash protection, an automotive design engineer would look at what's happening to my steel structure upon impact, and how can I get as much dynamic deflection as possible to, like the example of cradling that egg. I want to get the number of G's as low as possible by allowing it to crumple so that the occupants don't feel that high reaction force. So there's different methods that are used for that.
Great. Well, thank you very much, Chris. I appreciate all the great information, and I'm sure all of our attendees did too. I think that's about all we have time for questions today. Thank you, everyone, for attending the webinar this afternoon. And we especially thank ITT Enidine and Chris for the great presentation. This presentation will be emailed to everyone later today and will also be available at www.designworldonline.com. Thanks for joining us, and have a great day.